Hello, everybody. Welcome to my talk. Thank you for taking the time to join. It's a great honor to be giving a keynote at SCAM. I've been involved with SCAM for very, very many years, and I enjoy it. I'm unhappy, though, that we couldn't all be together this year, that we have to do this remotely. However, I'm still going to enjoy the experience, and I hope you all will too. So what I'm going to be talking about today is advanced static analysis and how it's become commoditized over the years based on my personal experience. So without further ado, I'm going to take a sip of water and get started. So here's my thesis, which is that advanced static analysis tools, which have been around now for quite a while, have been successful and they continue to be useful, but their core unique value, I believe, has been somewhat diminished by this commoditization effect. So I'm hoping to tell you the story about how this came about, so that in the hope that you will enjoy it and you will find it interesting, and that if you're getting into your own static analysis work or setting up your own startup, that it will help you develop it. So I'll start with a little bit of background. So I've been at GrammaTech now for almost 30 years. During that time, I've been working mostly on things having to do with software analysis of one form or another, mostly static analysis, though, in C and C++, also binary analysis. Way back, we had a static analysis tool that worked for Ada. Most of my work recently has been in CodeCenter, which is our flagship product, and it is an advanced static analysis tool. We sell it mostly for doing C analysis and some C++ analysis to the safety-critical embedded market, and we do that worldwide. These are organizations for which failure in the field is sometimes very hazardous. People can die, and so on. I've also worked on other software engineering tools, slicing, language-sensitive editing, and so on. More recently, software composition analysis is something we're getting into. So these remarks are my personal opinions, and there's a lot of opinion here, not so much backed up by evidence. It's because such evidence is hard to come by. So it's based mostly on my opinion and experience. So here's my outline. So I'll give you an idea of what it means, of what advanced static analysis really means to me, and the history of the tools in this domain. I'll give an example from CodeCenter, just to give you a feel for the kinds of things I'm talking about. Then I'll talk about these commoditization effects and how they've taken hold, starting with lists and standards and so on. I'll talk a bit about benchmarking static analysis tools and how that has had some unintended consequences. Then I'll talk about how the core value of these tools, which is finding the serious bug, has been kind of overtaken a little bit or crowded out by more superficial things. And I'll say a little bit about how the commoditization effect has taken hold and what we can do about it. So a little bit of history. So you're all probably familiar with some of the early generation of static analysis tools. In the beginning, there was lint for C to compensate for what I call the radical libertarianism of that language, where you could do basically anything and there was nothing or very few safeguards in place to prevent you from doing really, really unsafe and hazardous things. Lint brought stronger type checking, a little bit of style checking, and the ability to find some undefined behavior. The stuff that was easy to find, it could find, but not the hard stuff. So it was useful, and these tools continue to be useful, but they are limited in scope. They don't find very interesting things for the most part, at least the kinds of things that we might think of as interesting. And there's a lot of busy work if you want to get lint clean. That you have to go through a lot of work annotating your code and setting up configurations and so on. But the key shortcoming of lint and the family of tools is that they're incapable of finding the most serious bugs in C. So advanced static analysis was a reaction to several things, several confluences. So first of all, there were the original sins of C, and I think of those as being undefined behavior, lots and lots of it, very easy to accidentally stumble into and very difficult to avoid. Then there's critical unspecified behavior because the language itself the specifications are ambiguous, so lots of things were left up to the compiler. And of course, there was unsafe typing. And as a consequence of these three original sins, there were far too many very serious defects found in critical software, operating systems, embedded devices, and so on that led to very serious security vulnerabilities worldwide that affected a lot of people and were very, very, very expensive. So C is, of course, very easy to abuse. We had these huge legacy code bases, like I said, operating systems and the like. And at the same time, lots of new C and C++ was being written, and so we wanted to avoid those. And the existing techniques were clearly incapable of finding the most serious defects because the most serious defects were cropping up all over the place in production code. So in the early days of advanced static analysis, the tools were focused on the 5 worst defects in C. And to us, these meant buffer overruns, which at that point was termed the bug of the century. And judging by the fact that we're 1/5 of the way through this century and it's still an extremely prominent bug in C, maybe it's going to be the bug of this century as well. Then things like dereferencing invalid pointers like nulls and the like, and then things having to do with memory management. Now, it is the case that most code works perfectly well most of the time. So a lot of bugs of these form escaped detection because it wasn't because they were easy to detect, it was because they were hard to detect. Because they were maybe interprocedural, they were a cross-compilation unit, they were whole program, and often they were on paths which were rarely executed. Now, buffer overruns, of course, are still a plague. If you go and look at CVEs and just search for buffer overrun, about 8% of all CVEs mention buffer overrun in one form or another. So it's still with us, and it's still a huge hazard. So advanced static analysis came along, focused on finding these most critical bugs. Now, I call these the high-value findings. You'll hear me say that term a bunch of times, high-value findings. The key point about advanced static analysis, though, is that it was focused on bug mining, not bug elimination. It was not a tool that you could use to eliminate all possible bugs. It did not give you any guarantees that it would find all possible bugs, because such claims were at that time and still are infeasible, or rather impractical for a lot of programs. The key technical properties of these tools is the following. So abstract interpretation based, that is, they would do some kind of simulated execution of the program using some kind of abstract domain, not necessarily the kind of very formal sound abstract interpretation that some of you may be familiar with, but abstract interpretation all the same. They were, of course, interprocedural, whole program, sensitive to context, flow, and path, and aware of APIs. That is, they had knowledge of key points in the domain of APIs that were important. So not just the C library, but also libraries like operating system libraries and the like. In terms of their usability, their key properties were they had good precision, that is, not too many false positives, easy to run, easy to understand the results, and they scaled to literally millions of lines of code. The tooling from around 2000, well, the tool space was dominated by these 5 tools. So Prefix from Intrinsa was one of the first. They were very tightly focused on a small number of properties. They ended up not having a huge impact on the industry, though, because they got bought out very early by Microsoft, who absorbed them entirely into their internal development organization. And they still use it today, and small parts of that tool, or the descendants of that tool, have made it out into more widespread use, but they weren't very widely known. The organization that did become very widely known was Coverity. Their tool was very successful. They got eventually bought by Synopsys, but before that they became the pioneer. They had very good technology, and they had extremely skilled marketing. Then there was Clockwork, which was also pretty popular around that time. We came along. Our first version was around 2002, I think, something like that. And then there were another class of tools that were more based on sound technology. That is, they claimed to guarantee to find all possible occurrences of certain kinds of defect. But this talk really isn't about those tools. It's about the previous four, the unsound tools. Now, the market reaction at that time was pretty interesting. So there was huge excitement from lots of customers. And what I'm showing here are paraphrases of quotes that I've heard from lots of customers, or that I've heard said about other tools. So for example, we've been searching for this bug for months, but your tool found it in minutes. We continue to hear that these days. So these tools were clearly filling a need at finding these very serious bugs. The other thing that it brought to light was that programmers, for the most part, did not understand undefined behavior very well. So people were doing things in their code that they didn't even realize was bad. And so having brought that to their attention, they realized it as much and reduced their risk accordingly. A key thing, though, is that a lot of people exposed to the results of these tools were kind of unbelieving. They didn't understand what was going on under the hood, behind the scenes. So they felt like it was a bit like magic. How could your tool possibly find this bug? How could it possibly have known what my intent was when I wrote this code? And so that was great. There was a lot of excitement that generated a lot of investment from government as well. So a very successful thing that they did in the early days was to fund Coverity Scan, which led to the very widespread dissemination of the capabilities of these tools. What that did was to set up a site where organizations involved in open source development could go and get scans for free. And it's still running today, it's still successful, but that led to huge adoption of this kind of tool industry-wide. Then the government standards organizations started to get involved. So NIST started the Static Analysis Tool Expo, which was kind of like a showcase where people could talk about how well the tools did on certain samples of code, and it was designed to popularize and spread the word among government organizations about how effective these tools were. They later got into the benchmarking activities, which I'll say a little bit more about later, which ended up having consequences that were unforeseen and not at all good. And of course, lots of other organizations or projects got set up for doing research into static analysis, including some at GrammaTech. So just to give you an idea of the kinds of defects that these advanced static analysis tools can find, here's my favorite example that I like to show from CodeSonar. So this is a cute example for several reasons. This is code that was found in the wild. It was in an open source game, like GNU Chess. It fits in one screen, and it's relatively easy to explain, but it also illustrates some pretty important aspects of the analysis and what's going on under the hood. It's also pretty amusing because if you look there on lines 2190 and 2191, there's a comment that says, boldly, this doesn't have buffer overflow vulnerabilities, yet there is a buffer overrun right in this code. This code was in the wild for many years before this bug was found. And so clearly the author had overlooked it, and any reviewers had overlooked it as well. And that's typical with the kinds of things that we find. They're often very difficult to spot by humans. Now, if you look closely on line 2193 there, that's where the flaw is. So there's a malloc there. It's taking Sterling of S, and then it's adding 1 to what gets returned from malloc. So clearly that's wrong. That +1 is on the wrong side of the parentheses because it's outside the parentheses. Whatever you get back from malloc, you'll add 1 byte to it, and the stir copy in the subsequent line is going to overwrite that buffer by 2 bytes. So what you see about this is, well, first of all, other static analysis tools had looked at this and hadn't been able to find it, but CodeSonar was able to find it because it models the heap, so it knows about malloc, it knows about strings, it knows about that strings have null terminators, strings have lengths, buffers have lengths, and it knows about cause to stir copy and that they copy so many bytes into a memory location. And furthermore, it knows that there's a relationship between the memory block that you get back from malloc and the stir copy. So all this is, having modeled all that, it falls out that there's a potential buffer overrun on that line. This code is also cute for a couple of other reasons. So there are some other bugs in this one function. So for example, on line 2193, where you call malloc, there's nothing to check there to see that malloc succeeded or failed. And it turns out that if malloc had failed, it would have returned 0, and the +1 would have turned that value into 1. So the regular check for whether malloc has succeeded by checking the return values for 0 wouldn't have worked here either. So as well as that, you've got a null pointer dereference on line 2194 that the tool also finds. So let's just give you a flavor. Let me move on. So as a consequence of this newfound popularity of static analysis and this new class of tools, the reaction was, well, this is great. Let's have more of it. And you can have more in lots of different dimensions. So people wanted the tools to find not just the high-value bugs, but other kinds of things, not just undefined behavior, but also API misuse, which is not necessarily as bad as undefined behavior, but can lead to undefined behavior, and also things like style violations, which are not necessarily even things that are correlated with bugs. Now, the early tools like lint and all, they've been finding things like that all along, but there was an expansion in interest in finding things like that after these advanced static analysis tools started to become more popular. And not just C and C++, for which these languages hit a sweet spot, but also safe languages like Java and C#, managed languages, and even interpreted languages like Python and JavaScript and so on. And then they wanted more API coverages, not just the language runtimes or the C library, but also frameworks and the like. And then what became a little bit corrosive, as I will explain, is more measurement. And that came in the form of lists and benchmarks. And of course, lots of organizations wanted to get on the static analysis bandwagon. Some organizations who'd never done static analysis before were claiming that they could do things that were similar to what advanced static analysis could do. And some of the compilers beefed up their static analysis, and the style checking tools like lint, they were suddenly claiming they could do things like what the advanced static analysis tools could do and be just as effective as them. So there was the bandwagon effect. But I think the list effect, or the effect of these lists and standards, the move towards measurement was a little bit more corrosive. So if you look nowadays for lists of things that are relevant to static analysis, then you find a lot. So the most popular of these is the OWASP Top 10. This is a list of things that you should avoid doing in mostly oriented towards web-based apps, things that you should avoid doing in the code. Somebody reminded me the other day that it should really be the OWASP Top 4 because 6 of those rules are entirely avoided if you just use a civilized framework. So maybe there should be one rule that says use a framework and that 5 of the other ones would go away. There's also CWE, which is essentially a catalog of bugs across multiple languages. At this point, there are, I think, over 1,000 CWEs. They're arranged in a hierarchy with inheritance, which makes things tricky, as I'll explain later on. Then you've got the secure coding guidelines, such as CERT and its predecessor built security in. You've got government standards, such as this is STIG. Then you've got secure coding standards, like MISRA C, C++, and so on, all of which were essentially subsetting standards. That is, they, for the most part, disallowed the most risky parts of the code, or established practices or rules that you must follow in order to avoid the most hazardous parts of the languages. Okay, so those were lists. Now let's talk about benchmarking, because I think this is one of the most interesting effects of this commoditization process. So benchmarking came along because organizations wanted to be able to compare tools against each other. In a competitive situation, if you can't turn to a benchmark, then your ability to compare tools is somewhat weaker. They also wanted to use benchmarks to be able to adjust tools and how they use them, to tweak their parameters in various ways to make them do better, either improve their precision, improve their recall, or other things like performance and so on. Then to find weak spots in the coverage or weak spots in the core engine so that they could adjust accordingly. The benchmarks, however, tended to be focused on 2 things only, precision and recall. Now, I haven't defined those terms, so let me just do that very briefly. Precision measures the ability of a tool to produce results which are true positives. So good precision means your results are mostly true positives. Bad precision means they're mostly false positives. And of course, everybody hits false positives, which itself has a bit of a corrosive effect, as I'll explain later. And false positives, by the way, with this class of static analysis tools, are impractical to avoid. So you have to deal with some number of them if you're going to remain a practical tool. Then recall is defined as the ability of the tool to find real bugs. So that's pretty important as well. But recall has this funny property where it's impossible to know ground truth for most programs. What these benchmarks avoided, though, was any talk of other important properties of the tool, such as its performance. Can you get the results back in a reasonable amount of time using reasonable quantities of computing resource? Scalability. Things like usability, were the results easy to understand? Could you act on them? And then things like robustness, which includes things like how well the tool fits into the environment, like is it able to parse various obscure classes of, various obscure dialects of the language and so on. And what came out of this was, through the efforts of the government, was the generation of a set of benchmarks called SAMET, and which is now Juliet, which contained thousands of both positive and negative examples of code that was designed to test the recall and precision of the static analysis tools. So most of what I'm going to talk about in the next part of the talk is going to be about, when I talk about benchmarks, that is about the Summit and Juliet benchmark. Now, benchmarks in general of this form had some key weaknesses that I found somewhat bothersome. So first of all, there's measurement methodology. So if you get thousands of samples, they're not going to be distributed across all the different dimensions in which you might hope equally. So for example, if you've got 1,000 buffer overrun samples and 1,000 samples of, say, unused value, and they're weighted equally, then you're not going to get very interesting results from running that benchmark. Now, I'm not making that claim that they're biased in any particular way. I'm just saying that a lot of these benchmark suites have a bias, and it's very difficult to remove that bias if you want to do a very serious comparison of the results. Then there's human error. So many of these samples were written by humans, and of course humans make innocent mistakes, even though they're well-intentioned. They make invalid assumptions, and they're inconsistent. So this means you get samples which aren't quite as good as you might like. We found several different errors in the samples that were in that benchmark suite. Then there are expectation mismatches. So the Summit, the Juliet test suite, is organized around CWEs. So you've got thousands of different samples in each CWE, and the expectation is that the static analysis tool will report warnings in terms of those CWEs. But unfortunately, that's not how all these tools work. The core flaw that the sample is intended to uncover might be in one CWE, but the downstream effect might be a completely different CWE. And if the tool is biased towards reporting the downstream effect rather than the upstream cause, then the measurement methodology is going to diminish the value of that finding. And that, in fact, is what happens in many cases. Then there's the tool configuration problem. So those that use these benchmark suites are really, really bad at finding the right configuration of the tool to run the experiment with. This is our experience time and again. So out-of-the-box configurations of tools are almost never the optimal configuration for any particular customer or any particular evaluation environment. The tools, we can't know in advance what our customers are going to be doing with our tool entirely. Maybe they're using a tool chain that's not the default tool chain. Maybe they're integrating with some set of tools that we don't expect. So we ship, and all the other tools do, ship with configurations that are intended to be a starting point for further refinement, but not necessarily the optimal point. Then the benchmarking of this form exerts rather unhelpful pressure on tool vendors. If your tool is going to be evaluated based on how well it does on a benchmark, then the tool vendors are going to naturally and understandably optimize their tools so that they do well on those benchmarks. Now, hopefully they are honest about that optimization, but I have it on good authority that when the government did a study using one of these benchmark suites, they observed that one of the vendors was cheating. That is, they were doing what Volkswagen did with their emissions. They were detecting that they were being run on the benchmarks and skewing the results accordingly, which is not great. Now, personally, my own opinion is that the fundamental weaknesses of the Juliet tests and similar are that they are based on what I call caricatures of bugs and caricatures of bugs are not real bugs. There's an assumption that they are good models of what is found in real programs, but in my experience, they're not. So here's why. So the benchmarks often start with really simple samples. So here's one, which is a buffer overrun of one word outside that buffer. And so if the benchmark suite contains a sample that looks like this, then the natural inclination of the benchmark suite designer is to vary it in various ways so that he understands the effect of those different variations in those dimensions. So for example, that sample is for an int. What about other types? Or what if the kind of the variable is different? This might be an automatic variable. It is an automatic variable. But what about if it was a global variable or a static variable? Or what if the buffer itself wasn't allocated on the heap? Sorry, wasn't allocated on the stack. It's allocated on the heap. Or what if there's other ways of expressing the base address or other ways of expressing the index? Or what if the entire structure, the entire statement is embedded in a control flow structure, such as in an if statement or a loop, or maybe it's across a procedure boundary. So these benchmarks are constructed in the form where you start with a little simple example and you vary it in various dimensions. So you can see that if you want to achieve coverage of only 3 variants in 6 dimensions, then you end up with enormous numbers of samples, which imparts an implicit bias in the entire suite based on the kinds of dimensions that you can vary for any particular bug, and plus simply the quantity of samples that you end up having. But furthermore, caricatures of bugs are not real bugs. So I assert that this code will never appear in any real program. It might occur in what a student might write, or what a very naive engineer might write, but then quickly discover and get rid of. And even this variance are unlikely to appear in that form in real code. So what I use as an analogy here is with facial recognition. So if you wanted to have a tool that does facial recognition and benchmark it, then you might what the static analysis benchmarking amounts to is somebody sitting down and making an abstraction of a face, and of course an abstraction of a face is a couple of eyes and a mouth, and it's a generally round shape. So that's a caricature of a face. It doesn't share any of the really significant, important properties of real faces. So then if you take it further and take that one caricature, what they're doing is doing things like saying, well, there's my sample, and let's make it a little different. Let's have one with glasses. Let's have one with a slightly different color. Let's have one with a mustache. Let's have one with a hat, and so on. So the way I see these benchmarks is that they're searching a space of caricatures for bugs instead of real bugs. And this has not had a good effect. So with that, let me back up to my thesis, which is that the very success of these advanced static analysis tools has led to this commoditization effect and the diminishment of their unique value. And just to be clear, what I mean by their unique value is their ability to find the serious bugs. Not their ability to find the superficial properties, but their ability to find the serious crashing bugs, the things that lead to serious security vulnerabilities, or planes falling out of the sky, or medical devices failing to work and killing people, and so on. That's what I mean by their unique value. So the effect can be illustrated by this kind of thing, this kind of animation here. So you've got your high value findings, and there aren't many of them because they're high value, but along come medium value findings, and so eventually along has come low value findings. And so what you're seeing here is the high value findings are being crowded out. Their value is being diminished simply by the large quantity of low value and medium value findings. So how does this come about? Well, it comes about through pressure exerted by customers on vendors that is a consequence of some of the things we talked about earlier. So so here's one thing the customers say to us. So they say, we must have static analysis. We recognize that static analysis is a good thing to have, but there's only budget for one tool. And furthermore, we've got lots of languages, not just C. Maybe we've got some Python, maybe we've got C# or Java, or even things like Perl. But we're only allowed to buy one static analysis tool. In many cases, the reasoning for this goes up to the corporate level. Somebody's making a decision based on a poor understanding of the actual ecosystem that the static analysis tool must fit into, and so they're saying, well, yeah, one tool seems to be the thing you want, and therefore I will only give you budget for one tool. Now, the effect of this is that if the customer is only going to buy one tool, then that tool, by definition, has to be very broad. And vendors who are investing in breadth have fewer dollars to spend on investing in depth. And if you're investing in breadth, then you're only going to get those low value findings, or you're not going to get very many high value findings, the analysis isn't going to be able to go very deep. Another pressure on the customer is this. So because of the lists, so you remember the lists I mentioned, the CWE and the OWASP list and the secure coding lists and safety critical coding standards such as MISRA and so on. Well, if you look at those, that amounts to hundreds of properties that the static analysis tool is then expected to detect. And the consequence of this, the effect, is that it kind of blurs or sometimes even eliminates the distinction between the high value findings and the low value findings. And then there's this pressure with the false positive hatred. Now, I get it. People hate false positives. I hate false positives as well. But the key thing is that you have to put up with some level of false positives. Otherwise, you're not going to get any benefit from the tool. From any tool, from any static analysis tool. False positives are just a part of life. Now, unfortunately, low value findings have typically pretty good precision. That is, if there's a warning generated by the tool, then it's likely to be a true positive. That's not the case with the high value findings. If you're reporting buffer overruns and 50% of them are false positives, then some people would indicate that, or some people would claim that that's a precision which is too low. They want their precision to be up in the 80-90%, but unfortunately, with the high value findings, you have to put up, in order to get the benefit of the static analysis tool, you have to put up with a lower level of precision if you're going to be finding reasonable amounts of them. So what this means is that the low value findings then tend to dominate the value of the high value findings. Other pressures, findings must be easy to understand. And this is even though the high value findings and the most dangerous and hard to find bugs are ones that occur along non-obvious paths. And the effect of this is that because the high value findings are much more difficult to deal with, they get they fall into this kind of confusion zone where the customer doesn't quite know what to do with them, but then they look at the low value findings and they decide that they're easy to deal with, so they give them more value. And finally, there's the move left pressure. So this is about moving left in the development process. Somebody said to me the other day, well, it's actually not move left, it's move everywhere. That is, get static analysis into everything, which means you have to integrate with IDEs, CI/CD, DevOps, code review tools, and then have a dashboarding app that sits on top of this that allows you to see the vast quantities of data that these tools generate. Now, unfortunately, what this means is that it's a little more difficult to integrate a high-value finding into some of these tools than a low-value finding. So, for example, a lot of the low-value findings are things that are associated with a single line of code. And if you've got an IDE that's integrated with your static analysis, then it's really, really easy for the IDE to pop up a little warning on that line of code that says you've got a problem here and explain it to you in completely. The high-value findings, though, often span multiple procedures. They're often along paths with complicated control flow, and they're often whole program. So you can't just put your finger on one line and say you've got the problem at that line. You have to bring in the whole infrastructure having to do with explaining the flow through the program in order to be able to understand that warning. And it's a lot more difficult to do that with integrations with things like IDEs than it is with single line warnings. So as a consequence of that, the high value warnings are much more difficult for the users to understand, and so their value gets diminished as a consequence. So that's my talk. Let me just go over my conclusions. So the key thing is that advanced static analysis tools have been around now for 15, 20 years, and they have achieved a lot of success. They are good at finding defects. However, that very success has led to their being commoditized. There are a lot of players in the market now. They're not all the same, and the pressures that are brought to bear on vendors have meant that the low-value findings that static analysis tools produce have come to dominate and somewhat eclipse the value of the advanced static analysis tools, which is, of course, is to find the really serious bugs, the bugs that cause the really serious security vulnerabilities or cause cars to crash and planes to fall out of the sky and so on. So I hope I've persuaded you that this has happened, and I hope you've enjoyed hearing about it. I would leave, though, with an optimistic tone, which is that there's lots of room for innovation. We continue to try to innovate in this field. In this very scam, we have my colleague Vineeth, who's talking about their static analysis approach to find bugs which are caused by parameters that are in the wrong order or otherwise misplaced parameters. So that's been pretty good and very entertaining. You will find, by the way, that that the number of bugs of that form found in lots of code is actually relatively small, which just backs up my thesis, which is that they are high-value warnings. High-value warnings tend to be rare, and so they are at risk of being, again, drowned out by the plethora of low-value warnings. Similarly, last year at SCAM, Vineeth and another couple of colleagues had a paper where they talked about a copy-paste error detector. Again, we think of this as advanced static analysis. It didn't really have to do with abstract interpretation. It was using an entirely different approach based on looking at lots of code and figuring out anomalies within that code. So there's plenty of room left for innovation here. So hopefully I haven't discouraged people from innovating, because I think there's still lots of opportunity to do so. And so with that, I will take questions.